Hello everyone, myself Varun Malviya and I am currently pursuing BTech in Material Science and Engineering from IIT Kanpur. Today I am going to introduce you to Clean Hull RL. This is an academic research project focused on creating a deep reinforcement learning AI to improve how we schedule ship maintenance. Specifically, this AI-driven framework is designed to optimize fleet deployment in the Andaman and Nicobar Islands. Let's start by understanding the baseline problem. The Andaman Sea has extreme warm waters, usually 27 to 30 degrees Celsius, which are rich in nutrients. This environment causes aggressive marine biofouling, which is when sea life rapidly grows and sticks to the bottom of a ship. Now, this growth creates physical drag in the water, forcing the ship's engine to work harder and burn millions in excess fuel. Now, to make the matter worse, ships have to travel a massive 1,200-kilometer distance for maintenance. Now, to solve this, my framework focuses on three main opportunities. Firstly, dynamic scheduling. Instead of guessing when a ship needs cleaning based on an old fixed calendar, I've used data-driven LLM models to schedule maintenance before severe damage. Secondly, localized oceanographic data. I won't use generic global estimates. I have used actual satellite data for sea temperature and salinity to calculate the approximate fouling rates happening at each specific island. Third one is the most important one, as it is the mathematical trade-off. My system constantly balances two things: the compounding daily cost of wasted fuel versus the massive lump sum cost of traveling 1,200 kilometers for maintenance. Now, what are the unique contribution of this project and how am I planning to scale it forward? Firstly, I am transitioning from historical to real-time ocean data. Currently, my framework has a unique pipeline that uses historical satellite data to calculate localized hull degradation. However, the next phase is to connect this directly to live data feed. Secondly, I have created a scalable economic translation. My project uniquely translates the physical friction on a ship's hull into actual daily financial deficit. Here I have used SARU class OPV as my baseline. I have used this class as the baseline because these ships are the workhorses of ocean peril. Because they are always in the water, they are highly exposed to biofouling. This makes them the perfect real-world example to measure how much extra fuel is wasted. Moving forward, I will expand this mathematical engine to include other major vessels. Finally, strategic UDA positioning. Right now, my model maximizes the defensive coverage for Indo-Pacific choke points 365 days a year. My ultimate future goal is to integrate this entire framework as a real-time asset for India's underwater domain awareness. Now, to make this all happen, my methodology has three-phase framework. Phase one is data ingestion. I have mapped the biofouling environment by taking historical satellite data from INCOIS, including sea surface temperature, salinity, and chlorophyll levels. This generates specific fouling progression curves for every island. Now, phase two is quantification. I have conducted an economic gap analysis using the fluid dynamics equation, and which allowed me to map the drag coefficient to the exact engine power required. Finally, I will calculate the fuel penalty per vessel. Now, phase three is the most important one, as it is the decision engine. I will take all this complex fleet scheduling and turn it into what's basically a high stakes turn-based board game. Every single day is a new turn. I will train an AI agent using reinforcement learning. Basically, I will allow the AI model to take turns and play to minimize the cost. At last, it will predict what we want. Basically, it will tell that the ship must hold its position, rotate with another ship, or send it in maintenance. Now, let's see who are the key beneficiaries. For fleet command, the AI agent provides uninterrupted 365-day operational readiness, securing the checkpoints in the Andaman Sea. This operation certainly translates directly into massive financial efficiency for the Ministry of Defense. On the other hand, ship repair yards can financially replace chaotic emergency dockings with predictable data-driven resource allocation. Finally, the framework aligns with Environmental Agency 2, as there is an active reduction in the Navy's carbon footprint and gain valuable data for tracking marine ecosystem health. Now, to wrap up, Clean Hull RL modernizes our fleet operations in three ways. First is automated logistics. It replaces manual gassing with smart AI-driven scheduling. Secondly is cost saving. It automatically balances fuel waste against transit costs to save money. Third is mission dominance. It ensures our ships stay in true shape and ready to defend the Andaman Sea year round. That's all from my side. Thank you.